So let's look at two problems from the more advanced exercise. And the strategy for these will be fairly similar, but a little bit different. It's going to be a little bit more challenging. So let me first start by just rewriting each of these expressions added together. Now, we could follow the same strategy where we essentially just multiply the two denominators together to get a common denominator. And while that will work and you will get an expression that is the sum of these, it will often be very messy and it will often not be fully simplified. So, a different approach, which might be better for these, is to first factor each of the denominators. And from there, we can try and find the least common multiple between the two denominators. So, let's start by factoring. So for this first one, the numerator stays the same, but in the denominator, it looks like we can pull out a greatest common factor since they're each divisible by 3 and by x. So we can pull out a 3x, and here we're just left with x, and here we're left with plus 5. And of course, you can double check your factoring by redistributing the 3x to both terms to get 3x squared plus 15x, which is what we started with. For the second one, you have 7x, and we're going to rewrite this as a product of two binomials, but you might also recognize this as a perfect square of binomials. And the first term in each would have to be x, since we get x squared here. And the last terms, we know that this number and this number, these are going to multiply to 25, and they're going to add to 10. So let's consider what multiplies to 25. It could be 1 and 25. Could be 5 and 5. Could be when they're both negative, but they have to add to a positive number, so that won't be the case. And it looks like 5 and 5 makes sense here, since those add to 10 and multiply to 25. And once you factor, of course, you can multiply this back out just to double check that it's true. So from here, notice that this has two different x plus 5s, and this has an x plus 5, whereas this left one has a 3x and this one doesn't. So for this one, our common denominator, we can think of that as our least common multiple of these. So if we multiply this one by 3x and this one by x plus 5, then they would have the same denominator. So 3x times x plus 5 times x plus 5 would allow us to get the same denominator by multiplying by the least amount of terms or factors. So let's rewrite these, but with our multiplication. And again, just to summarize, we're multiplying top and bottom here by x plus 5 and top and bottom here by 3x. And that way, in both cases, we end up with this 3x and two factors of x plus 5. So rewriting by finding our common denominator. So for the first one, you have 4 over 3x times x plus 5. And we'll multiply the top and bottom by x plus 5 so that we can get that desired common denominator. And then for that second one, we're going to have 7x over x plus 5 times x plus 5. And here we multiply top and bottom by 3x. And notice by following this multiplication, we do end up with the same denominator in each of these. The order is different, but that doesn't matter with multiplication. So now that the denominators are the same, we could simplify all of this into one fraction, where that new fraction will have our common denominator, 3x times x plus 5 times x plus 5, which in this case I'll just write as x plus 5 to the second power, since they mean the same thing. Now up here we have 4 multiplied by x plus 5, and here we have plus 7x times 3x. And we just need to fully simplify this. So let's make some space. We'll work up here. And in the numerator, let's distribute. So this 4 goes to both. We get 4x plus 20. And over here, 7 and 3 is 21. X and x makes x squared. So you get plus 21x squared all divided by this 3x times x plus 5 squared. And just to make it nicer, let's just rewrite it, the numerator at least, in standard form. So the highest power term goes first, 21x squared plus 4x plus 20, all divided by 3x times x plus 5 squared. So our original problem, where we're adding these two rational expressions, when they do come together, we get this simplified expression here. Now, these can be a little bit difficult to check, but if you do want to go through a process, one thing you can try doing is just plugging in a number. Let's say when x equals 1, you do have to be careful. You can't plug in 0 or -5. But if we plugged in 1 here, we would get a value in the top and the bottom. And then we can do the same thing to our original fractions. Plug in 1 for each of these, simplify everything, and then add the expressions. And if you get the same value in each of these, you can feel pretty confident that this is the correct addition of those two rational expressions. So with that in mind, let's do one more problem. And it's going to be very similar. We're going to take the same approach. We're going to first rewrite it, and then we're going to factor each of these denominators so that we can hopefully find a common denominator that is a least common multiple of the two denominators. So after rewriting these two rational expressions, let's now factor our denominators. So this first one, we can factor in a product of two binomials. And since the first term is x squared, we can just write x and x. And our two missing number terms, we know they're going to multiply to 16, and they're going to add to 8. So let's look at the possible combinations. So it could be 1 and 16, 2 and 8, 4 and 4, or all three of these, they can all be negative, but we know they're going to add to a positive number. So it has to be plus 4 and plus 4. Now for our second denominator, notice we can pull out a greatest common factor. So each of these terms has x in common, so we can factor that out, and we're left with an x plus 4. So from here, we need to figure out what works as a common denominator. And notice we have two x plus 4s here, we've got 1 here, and we've got a factor of x in this one. So to make them the same, we'd need to end up with an x here and an extra x plus 4 here. So our common denominator, we need at least two x plus 4s, but we also need a factor of x, since we already have one here. So if we multiply top and bottom of this first expression by x, and top and bottom of the second expression by x plus 4, we would get our common denominator. So let's do that. We can work down here. And so we get 8x over, and I'm going to rewrite this as x plus 4 squared. We can multiply the top and bottom by x. And for this next one, we have this 6 over x times x plus 4. And we're going to multiply the top and the bottom by x plus 4. And that way, now notice they have the same denominator. We have two x plus 4s here and 2 here, and we have an x here and an x there. So now they're the same. And so we can simplify. We can combine it into one fraction. And in the denominator, you have x times x plus 4 squared. In the numerator, we can simplify this. 8x times x is just 8x squared. And in this numerator, well, let me just rewrite it as minus 6 times x plus 4, just to be careful, since we're subtracting this entire thing here. So really, you need to distribute the -6. And doing so, we still have 8x squared, but then we have minus 6x, and minus 6 and 4 makes minus 24. Everything is divided by x times x plus 4 squared. So this should be our final answer. But like I mentioned, if you want to feel very confident that you're doing this correctly, you can plug in some value. And let's say we can plug in x equals 1 again, since that's simple. Find what this would simplify to, and then go back to your original problem. your two rational expressions that you're subtracting, plug in 1 to each, carry out the subtraction, and simplify, and see if you got the same value here when you plugged in 1 as you do over here.